Heavenly Father, we thank you for this day. I thank you for all the students that are here and the ones that are coming. Just bless this class, Lord. In your name I pray. Amen. James, yesterday I intentionally called a Korean a Vietnamese to level the playing field. So, just to...
Yeah, it's fine. I think along there, I think a lot of statements will, whether you're from New York or downtown.
Oh. Nice insult. Let's see here. I'm sorry, are some of you from Tennessee? No? Okay, see? All right, so I've introduced, of course, complex numbers. Today, I'm going to start by talking about nth roots of unity. And so I'm sure there are many things I forgot to say last time, but probably chief among them is the fact that the complex numbers form a field. All right, what's a field? A field is a set of numbers which allows multiplication, addition in the natural way, and every non-zero element has a multiplicative inverse, right? Well, one of the things I showed you last class in your first homework problem is, in fact, to prove that any non-zero complex number has a multiplicative inverse, or you could say a reciprocal, right? Such that we multiply the reciprocal times the number, we get back to the number 1, right? So complex numbers are very special in the sense that they are a field. But they're more than that. As I mentioned, they're an algebraically closed field, which means any polynomial of order n actually has n zeros possibly repeated, right? So we can study the solution. We can say that here's some notation, definition. 1 to the 1 over n, what that's going to be is the set. Oh, you're fine, just go ahead. If you need to walk over there, it's not a big deal. It's fine. Yeah. I mean, if you want to sit there, it's cool. If you want to go over your usual spot, like, you just duck down. No one, I had two choices. I can start class late because it's not your fault. I understand convocation went long because it always does. Or I could go over time. So I chose to start class on time and, have this conversation with you now. And you, oh, wait a minute, you're coming. So 1 to the 1 over n, what does this mean? This is, all right, what this is z in the complex numbers such that z to the n is equal to 1. All right. Actually, this is part of a larger definition, which is that if we wanted to talk about the nth roots of, let's say, w, what would that be? That would be the set of z in the complex numbers such that what? Z to the n equals to w. Now you might say, what do you mean a set, right? Well, just before I get into the more general proof, let's just think about, for example, 1. What's this? This, by definition here, is 1 and minus 1. In contrast, we would define the square root of 1 in the complex sense just to be 1. So we're going to make a distinction between the principal root and the set of nth roots, right? Now, what I want to prove to you, okay, guys, is that, here's the theorem, that 1 to the 1 over n, these are called the nth roots of unity. What it is equal to the set 1 omega, omega squared, omega to the n minus 1, right? Where omega is the exponential of 2 pi I over n. And so sometimes if you want to, if there's danger of ambiguity, if you're talking about, sometimes you might adorn this with like a sub n, like that, just to say it's the nth root, the nth principal root of unity. Actually, not principal. Yes. Excuse me, principal nth root of unity. So this theorem I'm stating is that you can obtain all the nth roots of unity from just the number, well, from powers of the principal nth root of unity. All right? Okay, so let's look at a proof of that. Here's the proof. Consider f of z equal to z to the n minus 1. You'll notice, Sam, that I have been careful to abbreviate principal, as I have a certain spelling ambiguity in the notes. I have different principles in different places, Anyway, so f of z equals z to the n minus 1. All right, this is an nth order polynomial. The fundamental theorem of algebra says how many zeros does it have? N, right, possibly repeated. All right? So, observe that f of omega sub n to, let's say, the j power is equal to, well, it's equal to omega sub, it's equal to e to the 2 pi I over n raised to the j power, right? And then all of that to the n power minus 1. So all I did was I evaluated this polynomial at the jth power of the principal root. Now I use some properties of the imaginary exponential I told you last time that you could prove. And so what happens? We get what? This is actually e to the 2 pi I j, right? The n's cancel, because when you multiply that, n cancels with that n, right? Laws of exponents here. And then minus 1. But just to remind you, once more, what is this? This is equal to cosine of 2 pi j plus I sine of 2 pi j minus 1. Just to go back there and remind you once more, the definition of the imaginary exponential is cosine plus I sine, right? And what's sine of 2 pi j? Well, that's 0, right? What's cosine of 2 pi j for any integer? Right? This is 1. So 1 minus 1 is 0, right? So this shows that any power of the principal root is a 0 of this polynomial, right? Then by the factor theorem, it follows f of z is equal to z minus 1 times z minus omega times z minus omega squared z minus omega to the n minus 1. And it must be that 1 omega squared all the way out to omega n minus 1 does what? It has to be, I mean, why do I stop here? Why are there just n of these? Well, if you multiply them out, what happens? The leading term is what? Z to the n, right? So if there was another power of omega, right, which was distinct from these, then what would happen? I don't know. I guess there's different ways we could do the counting here. I mean, if you don't like this, we could say, go out, keep going out with powers of omega until you have, enough distinct copies of omega to get out to the nth power. Let's see here. But what I'm going to prove to you in just a second is that I think, well, when I looked at this yesterday, I convinced myself that this proved that there were at most n distinct roots of unity, right? Well, let me just say it that way. Could there be more than n distinct roots of unity? There could not, right? Because if there were, that would, by the factor theorem, imply a factorization with more than n plus 1 linear factors, which would contradict the leading term being z to the n, right? So there can be at most n distinct roots of unity, all right? Now, my claim is that these, in fact, are those n distinct roots. In other words, that there are no repeats. There are no repeats in this list. So how do I prove that there are no repeats in this list? So observe that as a set, the nth roots of unity, the size of it, is less than or equal to n. In principle, I mean, I guess we could have in principle, z to the n minus 1 could factor and have like a repeated root, right? And that's where strict inequality rather than equality there with n would come from, if there actually was a repeated root. I'm about to prove that there is actually no repeated root in this list. There's no two different things that could be grouped together and give a z minus omega to something squared, all right? So suppose zero is less than or equal to k, is less than j, is less than or equal to n, all right? And suppose that omega to the k is equal to omega to the j, all right? Towards a contradiction. Then that would mean that e to the 2 pi I k over n is equal to e to the 2 pi I j over n. Yep. What? I suppose, but oh, you're right. I really only care about n minus 1 anyway. But fortunately, so now you're right, though. I mean, the n the k I'm interested in are ranging between 0 and n minus 1. Fair enough. Oh, yeah, but I'm assuming k and j are distinct, so that you still can't have k equals to j, because I'm assuming. I'm not saying they're congruent mod n. I'm saying that they're distinct and are between 0 and n. Yeah. Okay, so then if we just multiply both sides by, let's see here, this of course implies that multiplying by e to the words. So this implies that e to the 2 pi I j over n times e to the minus 2 pi I k over n equals to what? And I probably should put the 1 over here, right? So multiply both sides by e to the minus 2 pi I k over n, so they cancel out and give you 1 on this side, and they give you this over here. But then, you know, by the proposition that I stated but did not prove, this is 2 pi I over n times what? Times j minus k. Right? But, and let me be a little bit more, let me finish this here. So what this is cosine of theta plus I sine theta, where what? I'm going to put the 1 again here just so we can look at it. We have this equation, cosine theta plus I sine theta equals to 1, where theta is equal to what? Yeah, 2 pi j minus k, a little bit more, divided by n, right? Okay, but notice that k minus j is what? Excuse me, j minus k is what? It's positive, right? And that is also less than or equal to n. Which you could verify through, I mean, it's pretty obvious. If you take two numbers between 0 and n, and you take their difference, they can't be more than n, right? So we have that, and then that implies what? That implies if we multiply this inequality by 2 pi over n, what does it give you? Right? In other words, theta is what? Theta is between 0 and 1. No, theta includes the 2 pi. I define theta including the 2 pi. Oh, I got you. Yeah. Fair enough. Uh-oh. Hope this doesn't get me into trouble.
Yeah, that's why you need it to be strictly less than n.
Yeah. Fair enough. And we do have that, right? So I just was rebelling against your commentary, which I should know better than to by now. I thought I had this thing pinned down last night when I wrote this, but there's always some kind of fly in my ointment. His last name is his step. Let's see here. No, I'm just kidding. Although if you were to be an insect, what kind of insect would you want to be? If you had a choice. Grasshopper. I'd like to be a praying mantis personally because I think they look really cool. Or maybe a stick bug because you could be like, I don't know. All right, I digress. So what do we need? So we're looking for cosine theta equal to 1, right? Sine theta equals to 0. And this condition. Is that possible? Now I rely on our knowledge of right triangle trigonometry. I mean, just basic trigonometry, right? Here's your sine, right? Here's your cosine. I should have done those in different colors. Oh, well, I'll dash it. And we're not including the 2 pi, right?
We're also not including 0.
Are we not including? Oh, yes. Thank you. I keep trying to ruin a good thing here. So what is it possible, is there any solution to that? Can we have cosine of theta be 1, the dotted thing be 1? No, I mean, cosine theta can't even be 1 in there. There's your contradiction. Cosine theta is not equal to 1 for 0 less than theta less than 2 pi. Hence, contradiction, and omega j is not equal to omega to the k for j not equal to k in the range of consideration, right? And there you go. That proves that the nth roots of unity are, in fact, what I listed. All right? Yay. It's pretty easy to prove that that list are all roots of unity in the sense that if we take the nth power of them, we get 1. The proving that they're distinct is what's, I think, more... what's wrong? No.
No, I just have a question. It's on
This one.
the step where you go from having the whole thing raised to the n minus 1 and then the n goes away. Can you just explain that again? It's on the second line.
Like go from...
Second line. Yes. So it's all raised to the n.
Oh, yes, this is because if we have e to the I theta raised to an integer power, that's e to the I theta. You just multiply. That was part 3. I called it the
Well, I understand that part, but
Okay.
then it's also raised to the n. But then on the next step, there
Yeah,
is no
it's-
n.
Right, there's 2 applications of it because the first brings in the j, and then outside that there's an n, so it's... And I'm not using theta in the same way, I don't guess. Here, the quote-unquote theta would be this 2 pi over n, right?
Oh, it's two pi.
So the 2 pi over n and that n, they cancel. Yeah. Or reduce if you like. All right, so let's work out the more general problem. So the question I have is, what about w to the 1 over n? What's the solution set? What are in the nth roots of w, right? And so it's a great chance for us to use the polar representation. So let's suppose that z is an element of the nth roots of w, right? And we'll say z is equal to r e to the I theta, and we'll say that w is equal to rho e to the I. I could put a phi or a beta. What would you like? I think I should put beta. I think it's easier to see the difference, right? Okay, so we're trying to solve z to the n equals to w, right? That's what it means for z to be in the nth roots of w. So then all we got to do is plug in the polar representation, r e to the I theta to the n is equal to rho e to the I beta, right? Now notice that r and rho are both real numbers, right? They're the modulus, or the absolute value, if you like, of z and w respective. We use de Moivre's theorem and a little bit, well, anyway, properties of algebra here. This is e to the I theta n, rho e to the I beta. So we have these two numbers are equal in the complex numbers. That implies what? They have the same direction and they have the same magnitude. Same direction. So I get 2 things from this. One thing I get is that r to the n is equal to rho. The other thing I get is that e to the I theta n is equal to e to the I beta. So that tells me what about r? So this implies that r is simply the ordinary nth root. And this is unfortunate, but it's just unavoidable. Sometimes we have to, I don't know, I mean, in context, you have to understand this means the ordinary nth root in the real sense. All right, rho here is a real number. I mean the positive nth root in the usual sense of real analysis. All right? I don't have a separate notation for that, unfortunately. So we just have to understand in context when we mean that. But it's not, actually, I say that, but there's no ambiguity because when we define the principal nth root here shortly, it's going to agree with my usage here anyway. All right. What I'm trying to say is we define the symbol nth root of a complex variable in this lecture, and it will reduce to the ordinary nth root in the context it has a real input. So there's no danger in the notation. What does this say? This says that theta n is equal to beta plus 2 pi k for some k in the integers. Right? I mean, we don't have injectivity. We just know that they at most differ by some 2 pi multiple. Integer multiple of 2 pi. Let's see here. A different way we could say this would be what? This would be e to the I theta n minus beta equals to 1. Oh, that's not helping. I'm sorry. I've lost my way here all of a sudden. I mean, this is what I wrote above is fine. It's just I'm forgetting something here. Words. All right, so we're trying to, what are we trying to find? We're trying to describe theta. So this says that theta is equal to beta plus 2 pi k over n, right? Okay, great. Thus, z is equal to the ordinary garden variety nth root of the modulus of w, which is called rho, times e to the I beta plus 2 pi k over n. Let's clean that up a little bit. So what that is the nth root of the modulus of w, or the absolute value of w, like that, right? Because that's what rho is. And we can do a little arithmetic here, right? What do we got? We've got, see this? What is this? Split off the part with k. What do you got? You've got 2 pi I over n, right? So this part of it is omega, I called it omega sub n to the k power, times e to the what? Use some color coding here. Which part did I just split off? This piece is coming from this piece, okay? What's left over? E to the I beta over n. What is beta? So here, beta is an element of the argument of w, right? So without loss of generality, I could assume that beta is the principal. I mean, you could put anything in the argument of w there, and you'd have a solution, right? So I would suggest then that if we write z equal to the nth root of the modulus of w times e to the I argument, principal argument of w divided by n, right? We take that, right? And then we just multiply by omega n, omega sub n to the k power. And that's a pretty good way to describe a typical solution of z to the n equal to w. Because all we have to do is think about k going from 0 to n minus 1, and that will generate n distinct solutions, because we know that the omega to the power k is distinct for different k. And the thing in parentheses is so important it has a name. This, in parentheses, is by definition, this is the nth root of w. the principal nth root of w. So you don't have to use w for that. Definition, the nth root, the principal nth root of z is likewise defined to be the ordinary garden variety nth root of the modulus of z, or the absolute value, and then e to the I principal argument of z divided by n. Okay? And so what's, just to come back to my question, what is w to the 1 over n? Can you tell me? We have just proved that w to the 1 over n is equal to, well, it's equal to the nth root of w, right? And then omega times the nth root of w, and omega to the n minus 1 times the nth root of w. So all you got to do is find the principal nth root and then just multiply by the nth roots of unity. That generates the whole solution set. Let me do this for a specific example. Make sure you guys are on board with what I'm saying. Let's calculate the fourth roots of, say, 1 minus I. Hopefully this is not a homework problem. If it is, so sorry. So what we have to do, what is this equal to? I mean, this is going to be a set with 4 things in it, right? So I've got, in this case, w equals to 1 minus I, which is equal to the square root of 2 times e to the what? E to the I. What's the principal argument of 1 minus I? Yeah, minus pi over 4. Right, that's between minus pi and pi included. Remember, we want to have our pi. By the way, there are typos in the notes. More substantive than the one you mentioned, Sam. Sam was complaining about my spelling of principle, which has been complained about before. But the more serious error I have in my notes is I define something called argo. All right, arg alpha, actually. Arg alpha of z is what? This is defined to be arg z intersect. That's still not the right thing, because it's not a set, it's a value. It's theta. Dang it, it's just... Oh. How can I say this? It's equal to theta, where theta is an element of the intersection of what? The argument of z and the set from alpha included to alpha plus 2 pi excluded. All right? In contrast, the principal argument of z is theta, where theta is an element of the argument of z intersected with what? Minus pi excluded and pi included. So the exclusion-inclusion is for arg sub alpha versus the principal argument. But these are both standard notations. So my point was, in my quest to make things part of a unified story, I have a couple comments in the notes where I say, arg sub minus pi is the principal argument. No, incorrect. You can't. These are potato, Baptist and Presbyterian. I mean, I don't know, whatever you want. I guess they're compatible. But I guess it depends on how pretty she is. Let's see here. What's that? Sorry, I digress. Don't think I need to edit that. Do I need to edit that? It's debatable. Anyway, my point is to you that there's typos in the notes right now about my my zest, my zeal to include the arg sub alpha as a special case of, or rather the principal argument as a special case of the argument which starts at alpha. We like to look at arg sub 0 because often that's the kind of angles we think about, right? When you think about geometric angles, you what? 0 included all the way to 2 pi not included, right? And that's what arg sub 0 would return to you. Standard angles between 0 included to 2 pi not included. You're being awful fussy about this. Does this really matter? Yeah, it really does. Okay. Getting back to the story at hand here, so minus pi over 4, the modulus is root 2, right? So what is the principal fourth root of w? It's equal to the square root of 2 to the 1/4 power in the ordinary sense, and then e to the I times minus pi over 4 divided by 4, right? Unfortunate it is that I chose a number that has a 4 in it for its standard angle, but oh well. Okay, so we got 2 to the what? To the 1/8 power in the real sense, right? And times e to the, what we got? Minus I pi over 16. Yeah.
Can you explain how you got from after the 1 minus I equal to the square root of 2? Like, I don't understand how you got the square root of 2 e to the I to the negative pi over 2.
Geometrically, because the standard angle here is minus pi over 4, as it was pointed out by one of you guys. And the length of this is the square root of 1 plus 1, which is 2.
How did you know that's an equal?
Because I looked at it.
Like, you can just pick one?
This triangle is 1, it's 1. And it's down, so it's minus pi over 4. Yeah, it's just polar coordinates. Now, this is dangerous, right? Because 2 to the 1/8 I've just defined to be a set of numbers. And yet I mean that to be a specific real number. So what do? You know, this is a problem of the notation. Maybe I should write, I mean, to be careful, I should really write this here in my notation, all right? Because that unambiguously is a single value, which is the real eighth root of 2. All right. And there you go. That's the principal nth root of w. What are the other 4 solutions here? What are the other 4 things in this? 1 minus I to the 1/4. Well, it's equal to the eighth root of 2 times e to the minus I pi over 16. And then we have, by the way, so what is omega sub 4? It's e to the 2 pi I over 4, which is e to the pi I over 2, also known as I. Because cosine of pi over 2 is 0 and sine of pi over 2 is 1, right? So so that's pretty neat. To generate the other solutions here, we just have to multiply by I, right? So I'm going to get very tired of writing this again, so I'm just going to call this Pac-Man. So we get I Pac-Man, I squared Pac-Man, and then, of course, I cubed Pac-Man. Which, fine, if you want me to write explicitly, we could write this one would be the eighth root of 2, and I got to add. How many 16ths is this? Pi over 2 is how many 16ths? 8 pi over 16, right? So this one would actually be I 7 pi over 16. And then we have the eighth root of 2, e to the I 15 pi over 16. And finally, the eighth root of 2, e to the what? Add another 8, I get what? E to the I 23 pi over 16, right? Doing the arithmetic. Now, I've actually given you a presentation of the fourth roots of 1 minus I in terms of Argo angles. right? I mean, I gave you angles, oh, not quite though, right? See, I can't even, this one's at minus 1/16. I got a 7/16. I got a 15/16. I got a 23/16. See? So technically, I should probably, to make these all, you know, fit into, if I wanted them to fit into this sort of argument, right? If I wanted my answers to be in these kind of angles, I'd still need to like add 32 pi over 16 to the first one and get the, you know, the first one is actually the 8th root. I really don't want to talk to you guys much more about standard angles in here because I don't think it's interesting and I'm just going to confuse you. All right, it's better for you to face these issues in specific homework problems than my meandering in here. I've said enough. All right. Uh-oh.
For the example, how is or why is it just 2 instead of the square root of 2 for the modulus of W?
Why is it just what?
So the modulus of W, why is it 2 instead of the square root?
No, the modulus of W is the square root of 2.
But then in the formula it's under square root also. So is it like a double square root?
What? I mean, I have the nth root of the modulus of W here. Over here, when I wrote W, I have square root of 2. But when I calculate the 4th root of W, I put the square root of 2 to the 1/4 power,
Okay.
which is what gave us the 8th power. Right, there's the square root for the modulus, but then there's the nth root if we're working with the nth root function. Yeah. Good questions? All right, so with that, I think I will just define a few functions.
Dr. Cook, I have another question.
Uh-huh.
Over there, why is the I squared not a -1?
It is a -1, but I wanted to, I mean, it is. You could just as well write this, look. Fine. All right, what I was trying to do, I have a homework question where I ask you to write your answer in polar form. So I was deliberately putting all of these in polar form to try to give you an illustration of that kind of calculation. But left to my own devices, I would just say that this, you know, is I Pac-Man minus I Pac-Man and then minus Pac-Man. Other way around. I Pac-Man. What's that? It depends on the problem statement. In the homework, I asked you to give your answer in polar form. So no, you couldn't do that. Polar form is not allowed to have a negative radius, or much less an imaginary radius. Yeah, sure. I mean, I don't have the copyright. It's really more of a question for, I don't know. I'm not sure who that's a question for, but all right. So moving along here. So the principal nth root function allows us to solve the equation z to the n equals to w, right? I probably shouldn't have erased that, but oh well, it's too late. So another function you might consider is, another question you might think about is, what if you had z, I'm trying to think if I want to do it this way. I don't know. I'm debating whether I should write w equals e to the z or z equals e to the w. I'm going to do that, and then I'll probably have made the wrong choice. But anyway, how would you solve for z? Well, in fact, we say that z is an element of log w, if I recall correctly. I sprayed and then I didn't wipe. Kind of dumb. All right. That's not really a question. That's more of a definition, I think. Let me find my actual definition before I butcher it. All right, that is not the actual definition. Let me give you a better definition. Sorry. Actually, I'm going to take it back a step here. Definition. E to the z. This is. First of all, I probably should actually define the complex exponential, shouldn't I? So e to the z is e to the x plus iy, right? And so here's our definition of e to the z. That's e to the x times cosine of y plus I times the sine of y. All right, that is the complex exponential. All right. Then we define log of z. This is the principal logarithm of z, is defined to be the natural log of the modulus of z plus I times the argument of z. In contrast, all right, in contrast, the little log is a set of values. Log of z is equal to the natural log of the modulus of z plus I times the little argument of z, where we add a number and multiply a set by a number in the natural way. I mean, this is a set equality. So that's how we define the complex exponential. This is how we define the logarithm. I showed you how we define the nth root. We also define z to a power, the power function. Here's how that goes. Z to the alpha, all right, how we're going to define that. This is going to be the exponential of alpha to the little log of z. So this is again, actually this is again a set of values. Right? From that set of values, you can pick one, all right, and you can do what's called a branch cut. Is there a question? No?
What's the difference between the one with the log, the one on the left, and the one on the right? Is it just one of them's for sets?
The principal argument is a specific number between minus pi and pi included. Little arg is a set of values, all possible, angles. Yeah. So the capitalization matters. Sorry about that. Now this is a set of values. So for example, you can calculate things like I to the I. I to the I would, by definition, be e to the I little log of I. What's little log of I? Little log of I would be the natural log of the modulus of I plus I times little arg of I. What's the argument of I? The argument of I, little arg, that's pi over 2 plus 2 pi k, such that k is an integer. Now, in the case that alpha is a real number, this actually is not a set of things. It ends up just being one thing. All right, because if alpha is a real number, then when you sort through this, well, I don't have time to explain at the moment, but there are cases that you'd like where the complex power function is not multiply valued. It's just got one output. Like if you have an integer there, for example. Yeah.
So in cases where it's not real, does it have a number of possible values?
It does unless you decide to choose one of those values as your output. And you could do that, and that would be called taking a branch of it.
So it's not multiple, not just multiple.
Yeah. Yeah, that in this case it is. Yeah. All right. Well, anyway, there is much more to say in Chapter 2. I would like you to read it. I probably won't say everything I say in Chapter 2 in here, but I will decide some subset. So I'm sorry I spent too long on the nth roots today, obviously. So thanks, guys. Oh, Ryan?